Good morning, good afternoon, good evening to everybody. First of all, I would like to thank for having me here in this fantastic conference about the use of a MATLAB. I'm very happy to talk in this conference because I'm a huge user of MATLAB, not only for teaching purpose, but also for research. And I started to use it when I was a PhD student some years ago. So I'm Alessia Paccagnini from University College Dublin, and I'm a macroeconomist. And in particular, I'm a macroeconometrician because I work with time series data, with macro and financial time series data. And in terms of research, I really love to use MATLAB for estimating a huge model with a lot of dimensionality. And for this reason that I would like to talk about advanced topics in macro and finance to deal with big data and high dimensionality. We know that classical econometrics is failing to give us good result, in particular in terms of forecasting, because there is what is defined the course of dimensionality. And for this reason that today I would like to show you how is it possible to provide good forecasting, and in particular how we can rely on machine learning technique adopted to macro and finance for forecasting purpose. I will give you a quick overview of the models that we are going to talk and we are going to use in this exercise. And in particular, we are going to consider factor models, including in the autoregressive model. After that, we are going to use the Lasso and ridge regression and the elastic net regression, that is the hybrid model, the combination between Lasso and the ridge regression. I will give you 5 minutes slides about the theory behind this model and the intuition how we can use this model in the MATLAB environment. So in this exercise, we are going to imply these models to deal with high dimensionality, and in particular to forecast macro or financial series, depends on what is it, your target series. In terms of data, we rely on a data set provided by the Federal Reserve of St. Louis. And this data set was started by Michael McCracken and Serena Nghi, where they publish a paper on Journal Business Economic Statistics, where they use this data set to implement some important investigation in terms of macro and finance analysis. And this data set includes more than 100 time series, macro and financial time series for United States. In our exercise, we are going to forecast inflation, but you can change your target variable in your exercise, as well as other features, just to make easy the comparison among different coding. And so in terms of estimators, let's start with the ordinary least square error estimator, the OLS estimator. This kind of estimator is given by this very quick formula where we have the loss function that is also represented in matrix and vector format. So in our first exercise, we are going to include factors. And these factors are included in the autoregressive model where we have a variable, let's say the inflation, that's represented by y, that depends on the legs, on its legs, and the factors are added to the inflation as external variables. So how we can get these factors? So let's assume that we have our big data set and we decide to extract some latent variable using principal component analysis in such a way that we can improve the quality of our estimation to avoid the course of dimensionality. So these factors are latent information in our exercise. So we say that we have, first of all, OLS regression. The second regressor is a Lasso regression. So the Lasso regression is very, very similar to OLS in the sense that we have our component represented by the loss function, but also we have the penalty function. And this penalty function is represented by lambda multiplied by this absolute value of theta I. This lambda is the Lasso tiny parameter, and this absolute value of theta represents the component that is going to be shrunk. And in this case, some variables in our exercise will not be present because it could be shrunk towards 0. That is the main aspect of adopting this Lasso estimator. On the other side, machine learning, there is another important regression, the ridge regression. The ridge estimator is given by a formula that is exactly like the Lasso, but there is a new entry, the square value of the absolute value of theta I. We have this lambda that is, in this case, called the ridge tiny parameter. So in this case, we can avoid that our series are shrunk to 0 because there is this square value. So they will be very, very small, but never 0, like in the case of Lasso. There is a long debate. What is the best, Lasso or the ridge regression? So there are a lot of discussion, and for this reason that maybe we can rely on an alternative, that is the elastic net. The elastic net regression is a sort of hybrid model because it includes both Lasso and the ridge regression. So if we look at this equation, we can recognize again the usual loss function and the penalty function. And so the penalty function in this case is represented by these two components that are given by the ridge regression, because we have a square value, and we have the Lasso regression, the other side of this linear combination. So the elastic net is a sort of trade-off model in the sense that we can have both. We can exploit the good aspect of the ridge of the Lasso regression. So how we can implement MATLAB? So what do you need in your computer to work with the code that we are going to see together? We just needed to install an econometrics toolbox and the statistics and machine learning toolbox, and possibly the last version of a MATLAB, because there could be some functions that are not recognized with older version of a MATLAB. So now we are going to see how we can code. So now I'm going to move to MATLAB to make this lecture more effective. And moreover, I will, in the slides, you can find some interesting references. Are not exhaustive because there is always a long list of papers, books that you can read to understand what's going on here. But it's just a starting point to introduce yourself in this kind of a literature of the use of machine learning to deal with high dimensionality in macro and finance. So now I will move to MATLAB possibly. And before starting the coding, with the code that I prepared, I would like to spend a couple of minutes about the data. So in the folder that you can find here, big data _ Alessia Paccagnini, you can find a folder with utility that are some function recalled by the main script in MATLAB. And also you can find this folder where you have the data. And in particular, we are going to use this data set of Federici-Lewis. So the data used here are already stationary data. So as I anticipated before, this data set is very huge. You have more or less 100 34 time series for macro and financial data. And also you can find this series from 1959 until today. So in the dataset that we are going to use, we stop until February, but you can find the updated version online. So the dataset that we are going to use here is already with series transformed, because if you go on the website, and in particular, you can see here the Federal Reserve of St. Louis website, where you can download the dataset. And in particular, you can go directly on the page of Michael McCracken. You can download the current dataset. You can also download the paper written by McCracken and Guy, the appendix, and some MATLAB code. I will show you why they are so important. So in this case, the dataset, the current dataset, is represented by series that are not transformed, so are row series, okay? But for our exercise, we use the transform series. And the series are useful because they are implied to estimate our factors. So also the factors are already in your data, so you can find here factors. But if you wanted to update, you can just go here in this folder, open the code Fred factors, and you can find all steps in the script. So you need to load and label the Fred dataset, you can transform the dataset, and you can extract the factors. So here in this dataset, so you have all the structure that you need in terms of transformation. For example, when you have a 0 in the coding, no transformation. 1, you have just needed to take the first difference, otherwise you need to take also the standardization of a series or take the second difference. You have the set of dates here, and you can transform your data, you can remove outliers, and you can generate your factors. So here you can consider, according information criteria, 8 factors. So you can pick here your 8 factors. And you can make other features. For example, you can introduce other information criteria, you can change the algorithm. So this code is very, very useful, and I always suggest students to use this code to generate factors. So let's consider that we generate our factors here, and now we are ready to check our coding. So the first code that I'm going to show you is this factors model. So in this factors model, you have just an autoregressive models plus some factors. And we can read our stationary data, we can read our factors, and we can select some forecasting target. But as I said before, we are going to consider the inflation represented by consumer price index. And here, what is interesting is that we have our sample split in different parts. So we have one third that is the in sample, the estimation. The second 1/3 is the hyperparameter tanning, that is the validation, and the test called in machine learning, but in time series and forecasting out of sample, pseudo out of sample in our exercise, because we are not going to forecast the future, is always 130. So if you're curious, you can run and you can see here your test hind, train hind, valid hind that are of the same size. Okay. Okay, so I can remove. Now, let's see what happens. So we picked some settings. So we forecast one horizon, we include 12 legs. So we make a model selection in the train sample, in sample. So we use the Bayesian information criteria, and the rolling window that is used for forecasting comparison is given by 36 observation. And we include the maximum on 12 legs for both factors and a regressor for inflation. And we compare our forecast with the prediction documented by a random walk. And what is interesting here is that we estimate the first model with OLS, and we add to our legs of inflation the factors. And we estimate our model easily in this way. We just consider this OLS estimation. So what is down here is just a way to show you how you can implement the forecast. And in particular, the last part of the code is just a way to compare forecasts. So since we don't have a lot of time during the lecture, I will just show you some plots, but with this code you can perform some forecast comparison, some forecast tests that are very common in forecasting literature. For example, the Dibble-Mariano test, that is the most important, where you can compare if the forecast of a random walk of your model are statistically significant, different or not. So I think that it could be a good way to compare a forecast. So now I run the code that takes very few seconds. And what we get in terms of plot are the first, the comparison of the true and the forecast. And we can see that it's not so bad. This is the first, because the orange line is a forecast with a true value, and is not very bad, this result. And the other two plots are the cumulative root mean square error. So we compute the statistic to understand if we make a lot of error in our forecast and we want to reduce the error. And we compare with the random walk. And we see that in these terms, it's better to use this RD, this autoregressive diffuse index, that is the name given by Stokes-Watson to this kind of model with factors. And you see that there is such big difference, but it seems that in terms of cumulative root mean square error, this model is very good. So if we compare also our results in terms of rolling root mean square error, there are some periods where there is not such big difference, in particular during the start of 2010s, but usually there is such big difference. So to be more precise, we need to implement the Dibble-Mariano test, but you can do by yourself using the code. So now let's see what happens when you're considering the lasso. So in terms of lasso, we don't have a such big difference until there is the declaration of hyperparameters. So we need to declare our setting of hyperparameter, and what is different is here, instead of using LS, you are using the Lasso estimation. So Lasso is very, very quick in terms of coding and running. And as before, we get 3 plots. The first one is this comparison between the true and the forecast, and is not such big difference. And as before, with Lasso, we get this comparison, but here we are able to find that our result is not so very good for the Lasso as no, it's a very good, sorry, because yeah, we need to look, the blue line is very good for the Lasso because it's reporting less root mean square error, and again, this result is similar when we look at the rolling root mean square error. So now let's move to the ridge regression. So I started to run because it takes more time, because there are more hyperparameters to combine in the ridge regression. That is one novelty in our coding, because here there are more hyperparameters, including because we need also to consider the square value in the penalty function. And the difference is that we have this called training of the kernel ridge regression that substitute OLS and substitute the Lasso one. So we need, and as before, we need to consider there are these features about the forecasting with a different test as implemented before. And it takes more time because you are more parameters, and also when you have the evaluation, so in the out of sample, the algorithm is going to consider these different parameters. So here we are, our result that is in line to what we have found before. So there is not such a big difference between the true and the forecast. And in particular, in terms of cumulative root mean square error, we get a better result for our ridge regression than the random walk, and the same when you are going to see the rolling root mean square error. So last but not least is the hybrid model represented by the elastic net. So this model is very quick, like the Lasso, and here the main difference is that you are going to consider the hyperparameter combination given by the ridge regression, and you estimate using the Lasso, and you consider the training of the ridge regression. So it's just this combination. So we have this estimate on the expanding window. And in terms of results, you get exactly what found before. So the best model is always the other model, not the random walk, just for a few periods, the random walk, if we look the rolling window is better. So summing up, we were able to find that these models are very, very similar, and in particular, if we just use also the factor models, that is the easiest model among them, we are able to get a good result in terms of forecasting. So you see again here that the cumulative root mean square error is lower for already the autoregressive model with factors. So it seems that when we are going to use this kind of model, we are able to beat the random walk. And this result is something that is quite important and very useful, not only in academic research, but also for practitioner activities, for example, for policymakers in institutions and central banks. So I hope that you are really enjoying my lecture, and for any question, curiosity, do not hesitate to contact me. So thanks so much. Bye-bye. See you next time.